Now that we know how to calculate the cross product, let's try some problems that involve the cross product. Here we have asked to find a unit vector orthogonal to A and B. Now it doesn't say calculate the cross product, but we know that is what the cross product does. It finds another vector orthogonal to the two vectors that you put into that operation. But also, let's pay attention to the fact that it's asking for a unit vector. So not only will we compute the cross product, crossing the vectors A with B, but then whatever that is, we need to turn it into a unit vector. For problems like this, we're going to have a bunch of tiny calculations, and it's easy to overlook the fact that it says unit vector. So make sure that you read the question carefully, and then even after you finish the problem, you read the question once again. So we'll start by setting up our 3x3 matrix with I, J, and K in the top row. We'll fill in the vector A components right underneath. The B components go underneath that. And then we'll compute the determinant of this 3x3 by expanding along the top row. If I'm looking at the I component, then I need to multiply 2 times 4 and then subtract -1 times -1. For the J, I need a minus up front. If I ignore the J row and column, then I'm multiplying 5 times 4 minus -1 times 0. And then lastly, for the K component, if I ignore the row and column that includes K, I'm multiplying 5 times -1, and then I'm subtracting 2 times 0. And then we simplify. Now this vector is the cross product. It's definitely orthogonal to the vector A, orthogonal to the vector B. And if this were a test question, I would tell you, go back and check. If I dot this vector, my cross product, with A, do I get 0? Because if the vectors are orthogonal, I should be able to dot them together and get 0. And the same thing with the vector B. Once I'm confident that that's the correct the correct cross product, then I'm going to go on and finish the problem by turning that into a unit vector. To make the cross product a unit vector, I need to calculate the magnitude. So I square each component, add them up, and square root them. Now, the cross product has a magnitude of the square root of 474, and we could turn that into a decimal, but there's no reason to. Let's keep our answers as exact as possible. So you use this magnitude to divide off the cross product vector, shrinking it down to a unit vector. And maybe we'll call it something like the vector U hat. Now, this is a perfectly good answer, the way that it's written right now, using the standard unit vectors, saying that I'm dividing by the square root of 474, but there's many different ways to write the correct answer. I could do it in component form, where I multiply in that magnitude in the denominator. And of course, in the homework problems, it will specifically tell you how it wants the answer written, but on like an open-ended quiz or test, you could write either one of these and they'd be perfectly fine. Another scenario where you might calculate a cross product without being told calculate the cross product is when we're trying to calculate the area between two vectors. Now, the area between two vectors is represented using a parallelogram. You might think, oh, the area between the vectors should just be the triangle, but guess what? It's not. Somebody agreed a long time ago that the area between two vectors would be the entire parallelogram. So if we want to calculate that area, Let's think back to our high school geometry class where we learned the area of a parallelogram is base times height. And the base really could be any side you want, but it's specifically identified as the side perpendicular to the height. So if you pick the height, then you can find the base, or if you pick the base, you can find the height. So let's say that the vector u represents the base of our parallelogram. Then the magnitude of u will represent the distance along the base, which is what we'll use in our area formula. And if we pick that to be the base, then the side perpendicular to that is represented by the red line. And that red line can be found just using simple trigonometry. So we have the angle between our two vectors, or the angle between our two sides, maybe we'll call that theta. Using the magnitude of the vector v, or like the hypotenuse of this triangle that we've formed, we can calculate the opposite side of theta, and that would be magnitude v sine theta. So then the area between two vectors is simply magnitude u, that's the base, times magnitude v sine theta, that's the height. And we've seen this before, magnitude u, magnitude v sine theta. That's actually the magnitude of the cross product. So then the area between two vectors is just the magnitude of the cross product. In other words, we have two ways to calculate area between two vectors. We could use magnitude u, magnitude v sine theta, or if we don't want to calculate theta, maybe we're not given theta, then we could calculate the cross product, then find the magnitude of that. So we have two different ways to solve the same problem. Let's talk about another application of the cross product, the area between 3 points. We can connect any 3 points using two vectors. And so we're almost talking about the parallelogram problem again, except for we're looking at only half the area, because a triangle is only half of the parallelogram. So the area for a triangle then is almost identical to the area of a parallelogram. We just need to multiply by 1/2. So if we're given 3 points, our first step would be to find the vectors between any given 2 points. So I'll do P to Q, and then I'll do P to R. Calculate these two vectors. Now we're going to find the cross product between these two vectors. Set up our 3 by 3 matrix. Multiply it out. And we get the vector 1i plus 1j plus 1k. So that's our cross product. Now we need to find the magnitude of that. That'll be 1 squared plus 1 squared plus another 1 squared plus another 1 squared for the magnitude to be equal to √3. Now remember, that's not the triangle, that's the full parallelogram. The area of the triangle is going to be 1/2 of that. In other words, our final answer will be √3/2. Next, we're going to talk about the triple scalar product. The triple scalar product involves 3 vectors, the dot product, and the cross product. We know that the cross product can be calculated between the two vectors u and v using the 3 by 3 determinant that we have on the screen. So then if we're going to take that and dot it with w, it'll look like that 3 by 3 determinant, which is a vector. The output of that is a vector dotted with the vector w. So if we expand the 3 by 3 determinant along the top row as if we really were calculating that cross product, and we replace w with the standard unit vector notation, then we can see that we're going to multiply the corresponding components. So this first component, whatever that 2 by 2 matrix would spit out, we'd multiply that to W1 because those are corresponding components. And then the 2 by 2 matrix on J, including the negative out front, would be multiplied to W2. And then the 2 by 2 in front of K would be multiplied to W3. We would lose all of the I, J, K notation, and it would turn into a scalar because the dot product produces a scalar. Now from here, we're going to start to rewind. This, what we have, is almost identical to our cross product after we expanded along the top row, except for the I hat, J hat, K hat has been replaced with W1, W2, and W3 respectively. So we're going to, from here, kind of rewind and tuck that right back into a matrix. So the W1, W2, W3, it was in the same position as the I, the J, the K, so we put it back up in the top row like how the I, J, K used to be. So that being said, the scalar triple product can be calculated as the determinant of one 3 by 3 matrix, where you have the entries of each of the vectors in any one of the rows. If you change the order of these vectors, right now I have W in the top row, but if I moved it down to the last row, for example, it would change my result by a negative. So it does matter where it is, although if you're just looking for the magnitude of this output, the absolute value of your scalar that comes out of this, then you could put them in any order and then just take the positive result. One of the applications of the scalar triple product is being able to find the volume of a 3D figure called a parallel pipette. I have a picture up here of a parallel pipette, and because we're in vector calculus, we're describing this 3D shape by using vectors. So a parallel pipette is almost like a box, except for every face of this figure is a parallelogram instead of a perfect square or rectangle. So we've aligned vectors along each side of the box at one corner. So we have the vector V and the vector W making up the bottom of this parallel pipette. And then the vector U is the top side. It's not straight up and down, it's kind of at a diagonal, it's along that edge going up towards the top of the parallel pipette. And we know that volume of any 3D figure is just area of the base times the height. So looking at this figure, we need to find two things. We need to find the area of the base, and we need to find the height. So let's start with the area of the base. We can see that that's just the area between two vectors, and we know how to calculate that area. It's just the magnitude of the cross products. And that cross product, V crossed with W or W crossed with V, it creates a perpendicular vector that points straight up. So it's perpendicular to the base. So the cross product, that yellow is so hard to see. Let me try a different color. The cross product is going to point this way in red. That's W crossed with V, or V crossed with W. I'll use V crossed with W. That's what the picture says. It's pointing perpendicular to V, and it's pointing perpendicular to W. So the cross product is in that direction. To find the height, we're going to take the projection of the vector U onto the vector V. So we'll take the shadow of U onto that cross product to create the height value that we need. So the height is going to be the magnitude of the projection of the vector U onto V crossed with W. Multiply those two things together and we'll find the volume of our parallel pipette. But maybe we don't want to calculate each of these separately and then multiply them all together. If there's a substitution that we could make to simplify things, then maybe that's what we should do. So let's take a look here. We could replace the projection, the magnitude of the projection, with the shortcut that we use for that. So let's remind ourselves that if we're doing the projection of u onto v, for example, and we only want the magnitude of that, then we can simply calculate that by doing the dot product between u and v, and then dividing by one factor of the magnitude v. So let's go ahead and make that substitution first. Replace the projection magnitude here using the formula that we've seen before. But we're going to have to adjust it a little bit because instead of v, we have the cross product of v and w. So we're projecting onto that cross product. So wherever we had v here, we need to replace that with what we have in our projection. So that'll look like u dotted with the cross product of v and w, and then divided by the magnitude of v crossed with w. So we're just making a little quick substitution there to apply the shortcut for the magnitude of the projection. And then we're multiplying that, remember, by the magnitude of the cross product. And because we're doing the magnitude of these two things, we don't have to worry about the order of the cross product being different in these two factors, because magnitudes will erase any negatives that were inside of them. So those two factors divide off, and we find that ultimately to calculate volume of a parallel pipette, we just need to do the scalar triple product. Making sure that we take the absolute value of that scalar triple product. It is possible that you could come out with a negative value, so we want to make sure when we're doing the magnitude of this projection, for example, the dot product, u dot v, that needs to have absolute value bars on it. I forgot to write that there, so let's fix that, and then that means this would have absolute value bars on it as well. So our volume is going to be the absolute value of the scalar triple product. So using the three vectors that we have on the screen, assuming that those three vectors make up a parallel pipette, let's calculate the volume. So we'll plug each of these vectors into the 3x3 matrix. And then we'll take the determinant of that by expanding along the top row. Applying that out. Simplifying. -4 with -16 is -20. And then we have -20. So the 3x3 matrix determinant gave us a negative number, but remember we want to interpret this as volume. So we'll take the absolute value of that. Say that the volume of this parallel pipette is 40 cubic units.